Optimization of a function subject to a constraint. Example, optimize z equals to 4a squared minus 2xy plus 6y squared subject to x plus y equals to 72. In this kind of question, we have two functions. We have the objective function, that is the function to be optimized, and we have a constraint function. This x plus y equals to 72 is our constraint function, y z equals to 4x squared minus 2xy plus 6y squared is our objective function. Now, in order to optimize this kind of problem, the first step to take is to move the right hand side of this constraint function to the left hand side in order to equate it to 0. That is 72 minus x minus y equals to 0. Then find the product of this constraint function with the Lagrangian multiplier, that is lambda, then add it to this objective function. This is the Lagrangian multiplier, then multiply it by 72 minus x minus y and don't forget we are adding this to this objective function. So when we add that, we form the Lagrangian function. We have that in this manner. So this is the Lagrangian function. We have z equals to next step, differentiate z to respect to x, y and lambda. That is z with respect to x, we are taking the first order partial. We have 8x minus 2y minus lambda equals to 0. That's our equation 1, which is also our FOC. The first order condition, which is FOC, implies that the first order partial should be equated to 0 in order to obtain our critical value. So when we differentiate 0 with respect to y, that equals to minus 2x plus 12y minus lambda equals to 0. This is our equation 2. FOC, and when we differentiate 0 with respect to lambda, and that will give us 72 minus x minus y equals to 0. This is equation 3, which is also what FOC. So that's our first order condition. Now from equation 1 and 2, 8x minus 2y equals to minus 2x plus 12y, which is also what equals to, this is 8, which is equal to 8s plus 2x equals to 12y plus 2y, and that is 10x equals to 14y. So our x equals to 1.4y. This is equation 3. So when we substitute equation 3 into equation 4, From 72 equation 3 into equation 4, that's 72 minus 1.4 y minus y equals to 0. Minus 2.4y equals to minus 72. Y equals to 30. So that's the value of our y. And we substitute y equals to 30 in equation 3 to obtain our critical value x. X equals to 1.4 multiplied by 30, that is equals to 42. So these are two critical value. Now the next step is to take the second order partial. We are testing the second order condition using the determinant of the bordered Hessian matrix. This is the bordered Hessian matrix notation. So we have ZSS, which is the second partial of ZS with respect to x. So that is, when we differentiate ZS with respect to x, that is 8. So this is 8. ZXY, differentiation of ZS with respect to y, that is minus 2. We have minus 2 here. And GS, that's the differentiation of this constraint function with respect to x, that is 1. So we have 1 here. We have ZYX here, that's the differentiation of the second derivative of this FOC with respect to x, that is minus 2. This place is minus 2. And ZYY, that's derivative of, and we differentiate ZY with respect to y, that is 12. GY, that's the differentiation of this constraint function with respect to y, that is what, 1. And we have 0 here. This is 1. This is also what, 1. So we can see that this matrix is bordered by these derivatives. So the plane matrix, that is ZSS, ZYS, ZSY, ZYY, that is the plane matrix, is bordered by this derivative of the constraint function. So let us find the determinant of this bordered Hessian matrix. And don't forget, the condition is if the value is greater than 0, it means that the function is what is maximized. If the value is less than 0, the function is what is minimized. So the determinant of this bordered Hessian matrix is given as 8 multiplied by minus 1 plus 2 multiplied by minus 1 plus 1 multiplied by minus 2 minus 12. That is equals to minus 8 minus 2 minus 14. Finally, our results. Equals to minus 24. Now with this value greater than 0 implies that what the function is a relative, sorry, is less than 0